Let's now summarize what we have just learned about Maxwell's equations as they're related both in the regular formulation and in the covariant formulation. We have been able to show that the differential form of Maxwell's equations as given here are exactly equivalent to, derived from, the relativistic form, which is stated as partial mu f mu nu is mu naught. Of course, this mu has nothing to do with this mu index here. This is a constant, times the current J nu. And the dual equation, partial mu G mu nu, is equal to 0. These are called the homogeneous, these are called the inhomogeneous Maxwell's equations. We then showed that if we look at the electric and the magnetic fields as being derived from vector potentials in their normal version that we see, that this is exactly equivalent to writing f mu nu as the derivative of the 4 potential here. Finally, we showed the equivalence between the Lorentz force and Newton's equations in this form and in their Lorentz covariant form over here, where we have the time derivative of the 4 momenta with respect to tau, the proper time for the particle, is equal to the electric charge on that particle over c times f mu nu v nu. What we did not finish discussing was the concept of gauge invariance, which let us formulate Maxwell's equations in terms of the 4 potentials with the D'Alembert. And to do that, let's consider the 4 potential, A mu, being transformed into a new 4 potential, A mu prime, which is, by definition, A mu plus the derivative, the contravariant derivative, partial mu of a function lambda of x, y, z, and t. If we imagine such a transformation, then it follows that the f mu nu prime after the transformation is going to be the derivatives, the contravariant derivatives in terms of the new potential. This gives us, by substituting these terms in here, the regular form here, as we take the derivatives of the potential A mu, partial mu of A nu minus partial nu of A mu, plus new terms, which come from these partials incidentally, this is supposed to be just a minus sign here, and this is not supposed to be here. The partials of this term here, the scalar term, which gives us partial nu of lambda minus partial mu of lambda. But as partial nu is equal to partial mu, this is true because the order of differentiation does not matter. It follows, therefore, that f mu nu prime is equal to f mu nu, and the fields are unchanged by this gauge transformation. And this right here is the covariant form of a gauge transformation, where this is any function lambda. Now, when we say that the electromagnetic fields are unchanged, we mean the physics is unchanged, because the physics is determined by the electric and the magnetic fields. And if the electric and the magnetic fields are the same, the forces that will be exerted on the particle will be the same, even though the vector potential that gives rise to the electric and magnetic fields has been altered by this contravariant derivative of a scalar function. All in all, this concludes our overview of relativistic electromagnetic theory in its covariant form, and we have showed how we can connect that theory to the regular theory that we normally encounter in undergraduate physics. This has given us extensive practice with our covariant and contravariant indices, tensor notation, the indefinite metric, the summation convention, and all of these different things should be familiar to you by now. The practice on these indices is very important, so one should be sure that they are capable of going back and forth between the normal and the covariant formulations. I would be remiss if I didn't at least mention some of the elementary concepts having to do with general relativity. In particular, let's just look at some of the verbal things that we can consider. The first thing is a result that space and time are curved. Where do we get this conclusion? Well, let's consider a large rotating platform that's rotating with some angular velocity omega, and thus the velocity is going to be equal to v is going to be equal to r times omega. Now the distance around the platform at any given distance r from the center is equal to 2 pi r. Until at a large distance, when we get far from the center, the velocity becomes enormous, and we have a velocity then which becomes greater than c 1/10 of the speed of light. When this happens, as we know, we begin to notice relativistic effects, and the circumference becomes 2 pi r times the square root of 1 minus v squared over c squared. As we get our velocity large enough here, at a large enough radius, this actually approaches 0. So r times omega, as r times omega approaches c, the Lorentz contraction takes over and begins to dominate, so that eventually one can see that no matter how large r is here, when we get to v squared over c squared, and that's because v is increasing linearly with r here, eventually this term will become equal to c, and one can actually see at what radius that will happen for a given omega, and solve that equation. So it turns out that for circles that are very, very distant out on this rotating platform, that we have a very strange effect. The circumference becomes larger and larger and larger, and then at a certain point the circumference becomes smaller and smaller and smaller, until finally, way out there at some large distance from the center, the radius, at a large radius, the circumference around that circle is 0. Obviously the space is very extensively curved at that point, and this is a non-Euclidean geometry. We also have a time factor. And time, as we get out far from the center, begins to flow slower and slower due to time dilation. Consequently, this space-time in itself is curved in these accelerated frames of reference. Well, Einstein realized that if he was going to deal with accelerated frames, he was going to have to deal with a curved space-time, not just a space-time that had an indefinite metric and that appeared flat, but one which actually was curved. The mathematical theory of curved space-time were done by a large number of different mathematicians, but the predominant contributions were made by Riemann and by Gauss in the 1800s. The next thing that Einstein began to realize was that gravitation is indistinguishable from acceleration. And to do this, he really performed a thought experiment, and he imagined an elevator, and in this elevator people are closed off from the rest of the world, and one is asked to distinguish, is this an elevator sitting on the earth where we have a gravitational field, or is this elevator in outer space and accelerating upward with the acceleration due to gravity? Now, as we all learn in physics, the acceleration due to gravity is indistinguishable based upon what the mass of the object is. So for every mass in the elevator, in fact for all objects in the elevator, they behave identically in an accelerated frame as they do in a gravitational frame. There is one exception to this, and that exception has to do with a beam of light. I want you to imagine now that we have this elevator that's accelerating upward, and we take a beam of light and let this beam of light head straight across the elevator, and with the acceleration, the elevator accelerates out from under the beam of light, so that inside the elevator there's the appearance of the light bending downward in this accelerated frame. I want to compare that, however, to that same room that's sitting on the earth that's in a gravitational field. Since the photon that makes up light has no mass, and since the gravitational force, according to Newton, says that the force on a particle of mass 0 is equal to 0, it follows that there the piece of light would go straight across the room. So we would get a difference because of light, but because of no other particle. Now, if we consider light as having a mass of 0 as the limit of a photon or an object that had a smaller and smaller and smaller mass, we realize that there would be no bending, that there would be bending due to the gravitational field and the accelerated field that's exactly the same for every single particle in every single physics situation until one got exactly to mass 0. Then suddenly the one that had the gravitational acceleration rather than the actual acceleration would not bend and would go straight across the room. That seemed unacceptable to Einstein, and he said, if this bending is true for all accelerated frames, and it's true for all particles of any mass above 0, no matter how small, then I conjecture that particles even of mass 0 will bend as they go across the room in a gravitational field, even though that's in contradiction to Einstein's law of gravitation. Well, this was very radical because Einstein has already, with his special theory of relativity, totally destroyed the standard concepts of Newtonian space and time, the law of addition of velocities and other things. So it's now Einstein is making the statement that if we look at Newton's law of gravitation, F is equal to G m1 m2 over r squared, that this law is also wrong, because there must be a gravitational force on even a photon which has a mass of 0. If anything, the law is certainly an approximation and is true, but could not be exactly correct. So we now see that, first of all, space and time is curved in an accelerated frame and therefore non-Euclidean. We now see that gravitation is indistinguishable from acceleration so if accelerated frames give us a curved space-time and accelerated frames are indistinguishable from gravitation, it follows that gravitation will give us a curved space-time. And with this, Einstein realized that a theory of acceleration must also be a theory of gravity, and that both of these theories must give rise to a bent or warped four-dimensional space-time structure. And of course he worked on this theory between 1905 and 1916 when he published his paper on it. Here I've gone through some of those concepts and written them out. In the accelerated room, c is a constant and the light beam will appear to drop as it crosses the room. But in the gravitational field, of course, we have F is equal to G m1 m2 over r squared. The mass of this photon or neutrino or other object is going to have no mass, then there is no downward force, and light will go straight across the room. But in no other physical situation can we distinguish the two rooms, and it was at that point that Einstein concluded that we should have complete symmetry and exact symmetry between the two rooms, the accelerating and the one in gravitational field, and considered them therefore indistinguishable completely. The first way in which this was able to be proved was in the consideration of the bending of light. And we have to say, how much gravity do we need to bend light in order to prove whether this theory is correct or not? And it turns out to be an incredibly strong gravitational field like that near a star. How do we get light, a light source, on the far side of a star like our sun and still see it? Well, it turns out that, of course, we've got stars behind the sun, and that starlight would be presumably bent, and one can predict how much that bending would be, but it's not easy to see the light from a star right near the surface of the sun. That is, unless the sun were to undergo an eclipse, and one could use a telescope to see the star, it would then appear to be in a different position. That experiment was performed in Africa soon after Einstein's prediction, And in his prediction, he predicted exactly what the angle of the bending would be. Now, they knew what the position of the star was, and they could of course, know where the star should be. And of course, it would have, they were really looking for a star that was behind the sun, but had an apparent position over to one side due to the fact that the light actually curved around the sun and could be seen during the full eclipse. They did that observation and found that the light was bent in exact accordance with what Einstein had predicted. Therefore, this was an incredible result and earth-shaking in the sense that we realized that the last vestige of Newtonian mechanics, namely his gravitational theory, was incorrect, or at least an approximation. When we actually get into a theory of general relativity, we therefore must see that there must be a linkage between the way we describe the curvature of space and time and the amount of mass and energy that is in space and time. And the ways that we can relate those two is, first of all, it is the metric itself, g mu nu, which gives us our concept of distance between 2 points and angle, i.e. our geometry or our metric. That must somehow or another give us the curvature of our space-time structure. So we'll now move from a metric which is equal to +1, -1, -1, -1, to one that actually represents a curvature of the space-time. So G becomes a set of functions of space and time. And we have equations now that relate this metric and its curvature to the density of energy and momenta in the space-time, which can be realized through the metric tensor, through the energy momentum tensor T mu nu. We may take this up at a later time, but for now, all we wanted to do was to refer to these concepts. There is great difficulty in looking at how space and time is bent and warped and runs at different rates all over our space-time continuum, and at the same time becomes the foundation of all of the rest of our physical theories. When we get to quantum theory and time and space and momenta become operators, this becomes more of a quagmire. And even to this day, we do not have a definitive theory that general relativity is quantum mechanically correct. We're now ready to begin our introductory discussion of Lie groups and Lie algebras. And the first part here is just an introduction with some of the notation that we'll be using. And we need to connect what is called the Dirac notation for our linear vector spaces with standard notation that we're more familiar with. If we have a standard three-dimensional Euclidean metric, a linear vector space, we know that that linear vector space can be spanned in terms of, say, 3 orthonormal vectors like I, J, and K. And any other vector, say a vector A, can be written in terms of I, J, and K with certain components, as I've done here. Here we've written the vector A as AX times the unit vector I plus AY times the unit vector J plus AZ times the unit vector K. And in this formulation, these unit vectors that are perpendicular to one another form an orthonormal set. That is, each one is orthogonal to the rest. Their dot products are 0. And each one, when we take the inner product with itself, has a length of 1. Our metric here, G mu nu, Gij, is equal to 1, 1, 1. And our concepts of length and angle are determined by that metric, which is defined by the inner product. A dot B is by definition the sum over I and J of G, Ij, Ai, Bj. Here we do not make an extension at this a distinction at this point between the contravariant and the covariant indices. The reason is that this metric, it has all plus signs on it for both upper and lower indices, so there's no difference between a lower I and A upper I, or B lower I and B upper I. For this Euclidean space, it's a flat space with no indefinite metric, our G again is +1, +1, +1. Our length is defined in terms of the magnitude of a vector, the length of that vector, is the square root of Gij, Ai, Aj, square root. In other words, the Gij, Aa, really gives us the square of the length, and so to get the length itself, we write this as absolute value of the vector, or the length of the vector, as being the square root of this. The angle theta is given, of course, in terms of the metric as the angle theta between the vector A and B as A dot B divided by the magnitude of A times the magnitude of B. Once we have the angle between any two vectors and the length of any vector, we form our geometry. That gives us our entire concepts of both length and angle. But to deal with Lie algebras and Lie groups, we need a much more complex indexing method than is possible with these integers ij and k. Or even if we number these unit vectors, I1, I2, and I3, and our vectors with components A1, A2, and A3. The simple indexing is fine if we live in a simple n-dimensional space, especially if it's finite dimensional. But once we get to infinite dimensional spaces, and then certainly the numbering becomes more complex. We must use real numbers or whole sets of real numbers. Such a space with a metric is normally called a Hilbert space. That is, we have a continuous infinity of components and unit vectors, all of which are perpendicular to one another, and not just an infinite dimensional space, but one that has a continuous infinity of unit vectors. If you can imagine taking every point on a real line from minus infinity to plus infinity, and at every point along that line there's a different unit vector and a different independent coordinate, that would make sense if we think of something like a function. And a function is, of course, a vector in this very large infinite dimensional space. In our dealings with Lie algebras and Lie groups, we need a very complex indexing that leaves these integers behind. We also need a concept of what is called the dual space, as we'll now need to allow for complex conjugation as well as a metric.